All right. Hello, everyone. Thank you for actually staying for the last talk of the day. I know everyone's going to go back home after this, right? It's all exciting. So we'll try to wrap this up really quick so we can also head out. Cool. So my name is Micheal Benedict. I'm an engineering manager at Pinterest. I lead the engineering productivity team who focuses to improve experiences from code, build, deploys, and obviously what we're going to be talking about today is more about governance. And I have here with me Yongwen, who's the tech lead of the team. And we're here to share some great stories with you on how we helped improve or build a governance platform at Pinterest. So to get started, I'll go through my usual slides. First off, if you don't know about Pinterest, okay, it sounds like many of you won't. I'll just quickly share with what we do. Our job is to provide everyone with an inspiration to create a life they love. So Pinterest is all about creating unique experiences based on your interests and providing a path to actually pursue those interests as well. For example, recently I ended up cooking steak. I looked up some recipes at Pinterest and it really worked out well. In fact, some of those recipes were so awesome that I ended up buying the raw materials from Pinterest as well, which helped me create an amazing steak. But regardless, our job is to help you take some inspiration and actually execute on that to help create a life you love. And obviously, to showcase why this is such an important thing, we have tons of people who use Pinterest. We have over 300 million people who use Pinterest on a month-over-month basis. They have collectively created and curated over 200 billion pins. That's like the largest curation of pins or assets across the world. And they're all been categorized across 4+ billion boards. And our job is to kind of take that and help every engineer at Pinterest move extremely fast. So our job is to provide a fast, safe, and a delightful path from an idea to production without having anyone to worry about infrastructure. That's our job. So what makes this really hard? The Pinterest architecture itself. So Pinterest is not a simple system. I like to quote our chief architect who likes to think of this as a left and the right brain, where one half is like dedicated to analytics, where we take in so many different inputs and try to understand how we can help create the right inspiration for different sets of people. And the other half is more around the serving stack itself, which takes a lot of this content and data and helps serve that to tens and millions of users. You can clearly see at the top of the stack on the left-hand side, those are our clients who use the Pinterest app, both on the web and the mobile, and it's all powered by a large API service. And for quick context, those two are the largest services at Pinterest, monolithic Django applications, which exist even today after 11 years after its first commit. It's been hard to kind of get rid of them. So with that, you can also see that the layer below that, we have tons of microservices, which actually provide the core business logic for Pinterest. And all the way at the bottom, it's more or less our persistent store stack. All right, obviously, all that infrastructure, as complicated as it is, we have a huge footprint. So overall, like thousands of microservices, where we do over tens and thousands of deploys a day. These run on, again, hundreds of thousands of servers. And the batch system itself powers even more, like millions of workloads running almost on a monthly basis. And what's more interesting is, obviously, given the size of infrastructure, our costs are not small or low. So to give you a sense of how we actually divvy up how much we're using on the public cloud, this kind of gives you a quick overview of how our costs are actually divvied up. So for some context, Pinterest started on the public cloud from day one. Our founders, the first commit they put together for the Django application was deployed on AWS EC2, and ever since then, we've always been on the cloud. So we are probably the cloud-native company you could talk about. So this is kind of how our costs are actually divvied up. And what I'm here to talk about today is if you're running on the cloud, you probably know that it's not as simple as trying to figure out where your money is really being spent. And what adds to this complexity is when you start looking at each aspect of the cloud. So for example, we rely heavily on the primitive services which our public cloud provider offers, the compute infrastructure, instances, more or less. The storage infrastructure, which in this case, we're a big AWS fans. We run on S3. And finally, there's some other costs as well, which we can talk about more. But what really makes it complex, if we start to divvy up our compute costs, it starts all the way at the more foundational primitives like regions, and then availability zones, and then gets even more complex as you go up, like, okay, what are these reserved instances? What are these on-demand instances, spot instance mean? And there's these tens and thousands of different instance types which we have to grok and understand, and they all mean something. And it'll even complicate matters worse. Everything can be put together in concepts called auto-scaling groups, where it can scale up or down based on how you've configured your resources. And I imagine all of this makes it extremely complicated to understand how you're spending your money across so many different dimensions. And to be honest, we're not done yet. Even after that, you actually end up paying more money as you kind of transfer data in and out of your instances to different variety of services. So this slide really just shows you a complex view of, sure, you're spending money in compute, but in reality, it's going through all these different aspects or dimensions of your compute footprint. Just to give you an overview, the same applies for even storage. Storage is not easy. Just storing a file on S3 or any like GCS is not the same, because you have to pay, again, based on the dimensions of what you're trying to do. It could be stored in a particular region or multi-region. You're probably storing it on the standard buckets, or it could be on Glacier, and any other aspects or tiers of offerings from the cloud providers. So overall, I mean, it's hard. It's really hard to kind of grok and put all these numbers together and truly understand like where exactly the money is going. And that's the biggest challenge we had at Pinterest. We are so large that it became truly hard to understand three things: who is running what on the infrastructure, how does it all add up to a certain amount of cost or set of resources, and finally, what can we do to better understand and plan going forward for all these different resources? Apparently that was a GIF, by the way. So, all right, so infrastructure governance. That's our seal of approval, basically, to say that if you're saving money in our company, you should get that seal of approval, because we don't want people to be sending emails saying that I've saved tens of millions of dollars without actually vetting it up. So that is, props to my team to kind of put that together. So I'm going to cover like 4 specific topics along with Yongwen over here. So how did we build a platform of governance at Pinterest? There are 4 key pillars, as we like to call it. 1, visibility, getting insights into how and who's using what. 2, ownership. This is one of the most important things we'll spend some time talking about. How do you have a clear view of ownership of who owns what, all the way from resources to code to all different aspects of tools and systems. The third one being, how do you effectively plan budget and capacity? And finally, we'll just briefly discuss a few things on the optimization side, specific to Kubernetes, and how we're improving that front. Cool. So let's start with visibility. What is visibility? So there's going to be 3 aspects to visibility. And I'm sure everyone's probably dealt with this if you're running on the public cloud. There is provisioning. So how do you provision resources? You can use your API or different sets of tools like COPS or your own custom deployment or cluster management tool as well. The second thing is how do you inventory these resources? So you have provisioned some resources in the cloud. Great. Do you know actually where they exist and how can you view all of them? I'm sure the consoles do a good job in providing that data, but after you reach a certain size and scale, it's impossible to look at 100,000 servers in the same console page. And finally, how do you understand the state of these resources? Is it running right now? Has it stopped? Has it been killed? So there's a lot of content or information which is missing, which usually the consoles don't provide at a certain size and scale. So those are the 3 key things as part of getting visibility. How are you provisioning your resources? Can you inventory your resources and track metadata associated with it? And finally, how do you meter and understand the state of those resources as well? And resources over here, I'm using it pretty loosely. It could be instances. It could be buckets. It could be even pods. And with that, I want to do a quick plug. We had open sourced an inventory store at Pinterest. This is what we use. It's called Soundwave externally. Internally, we call it CMDB, Configuration Management Data Store. Not a very friendly name. But yes, this is what we use today, where we can query every instance running at Pinterest. We can get very precise metadata about when it was terminated, when it was running, like what was the configuration around it, all the way from network cards attached to it, to what kind of versions of OS we were running on it. So this has been an amazing store for us to keep track of things as and when instances come and go. And clearly, that lets us do things like this. We can truly understand, OK, given a number of instances, and you have all this amazing metadata next to it, how can you truly visualize what's happening within your company? This is just a quick Tableau visualization we put together just to show this footprint of all the services running at Pinterest. The blobs you see and the size of the blob reflects how many instances and CPUs they are using, essentially. So this thing does get complex the moment you get into Kubernetes, because when you're looking at instances, you do have access from the cloud provider on the APIs and metadata to tell you, when an instance came up, when it died, and other associated metadata. Now, to replicate that similar experience, it was important to look at Kubernetes and see what kind of primitives do we have in place to kind of leverage or create the same level of metadata so we can reuse our same system. So some of the key things we realized is that a lot of this data is ephemeral. It only stays for a certain amount of time within the Kubernetes cluster. So that was one of the biggest challenges we had to address, like to ship that information as quickly as possible to some sort of persistent store. And we ended up leveraging Elasticsearch for that to ship this to our inventory store. And that's kind of the key metadata we try to pull out from every pod. Like, what is the identifier? When was it created? When was it terminated? And we also track all the reservation information in terms of the resources requested by that particular pod. And all of that gets shipped to Soundwave. One thing you'll note, interestingly, there's a concept called identifier. Now, these are not pod names. And very soon, we'll actually talk about why this is one of the most important things if you really want to have a clear view of your infrastructure, from instances to Kubernetes to, it could be even Hadoop for that matter. How can you singularly try to understand how to identify these resources? And once you have this data in Soundwave, it was more or less an ETL job, which we ended up writing, called the Chargeback system, which pulled a lot of this data together and compiled information for us to tell us how resources are being utilized within the company. And what this lets us do is it lets us visualize this particular data in very different sets of dimensions. This could be from how many instances are running to actually who owns a particular instance, to even more data saying even more data around aggregation of which team owns certain instances or which organization owns instances. And what's the best part is, since all of this has been generalized, we can actually look up a given team or a given organization and not only see the instances they run, but also their Kubernetes pods, their S3 footprint, the Hadoop jobs they're running, all different platforms, all bundled up through a single chargeback interface. And yes, it leads to some fancy visualizations. So this is kind of the data our FinOps team and others track on almost a day-to-day basis to see how we're growing on CPUs. This is literally just, I think, 4 months worth of data, but you can clearly see the uptick in our vCPUs. That's the metric we use internally, just to show how we're prepping up for the holiday season. So all of them, each individual color actually represents a service or a platform. And I think it should be pretty obvious, like the large ones, what they essentially mean. Why is it hard to kind of track the large platforms? So one thing I do want to call out is that this is just an EC2 or an instance view of things. The next level of chargeback actually gets you details into why is that blue bar so large. So that is potentially either Hadoop or Kubernetes in this context. And we can actually do a deep dive to understand which pods or who's using what resources within that as well. All right. So with that, I'll actually have Yongwen talk about our next pillar, which is identity and resource.
Great, thank you. Thank you, Michael. Hi, everyone. I'm Yongwen from Pinterest. Can you hear me? Okay. Thank you, Michael. Hi, everyone. My name is Yongwen Shu from Pinterest. So I'll continue to talk about the other aspect of the InfoGov at Pinterest. So ownership, as Michael mentioned, that is the cornerstone of the governance. So we need to know that who owns what resource, and then how the ownership is rolled up to which organization, and then who spends what, that kind of things. And then also, actually, we want to know that what manager owns this resource, right, this project, right? That's very important things to do. Okay. To solve the ownership problem, we built our identity service called Nimbus. So we don't have a name here, but it's called Nimbus. And it has 3 components. One is the identity, and the ownership, and then the metadata. So it serves as a single source of truth that the ownership and associated metadata. So there's an example of the service on Kubernetes called Hermes that we talked about yesterday. So we have the ownership of this service at the Nimbus system. So it shows what the owner is as a manager, Micheal, and you also have the team email, and then the description. Also, there's some metadata associated with this service. So for example, we can easily find the Slack information. You can find the PagerDuty of this service, so that SRE can easily to page the owner of the service if anything that goes wrong with the service, right? Yeah. So let's take a quick look on how the identity is specified in Kubernetes world. So we implement this as the key to the identity is the canonical specification. So that's why we have this URI it's called unique resource identifier. So we have a specification that's always start with Nimbus, just like the HTTP, right? So Nimbus, and then you can put the project there, and then the platform, and then each platform we can have a slight different specification. For example, here then we have the Kubernetes platform, and then for Kubernetes platform we can identify the cluster this pod is running at, and also the workload type. So at Pinterest we use a lot of CRD, and then the CRD type actually we stored it in here, and then also the name of the application, the pod. So in this case that actually this information is stored in an annotation that is injected by our CRD controller. CRD controller will depend on the namespace, and then this service is belong to what project, right? And it inject this annotation in the pod, so that later on in the data injections, ETL pipeline, we're able to identify this pod, and then it's a utilization of this pod as well. Okay. One thing to mention is actually, because we use this URI format so that we can support multiple platforms that belong to a certain project. For example, then this service can also run on VM, right, the EC2 environment, so that you can have another resource that is called Nimbus, and then same project, my app, and then on EC2, and then the cluster and the stage as well. This way that we have a global view of a project, that what resource is belong to, and also we can add the S3, for example, or even if this project associates some Hadoop job, then we can also group them into the same project with a different platform, different resource. Okay, with this ownership system, then we can actually build tools around that, this the Nimbus service, right? One tool we talk about here is the SRE bot. SRE bot is actually a Slack bot, so that in Slack, you can run a command to do a reverse query on a project, or even on the host name or on the pod name. So from the host name or pod name, we can reverse query that what project this pod is belong to. And then from the project, we know which manager actually own this resource, right? And then if anything that goes wrong on the service, then we do a reverse lookup, then we can find the PagerDuty, and then we can page the person that's on call for this service. So it's very useful as this ownership tool. Okay, now we have the visibility, and then we have the ownership, identity. The next step is to look at the capacity planning. And because we have the history data, right, the capacity data, we can do a forecast. And then the gray line is from the planning, basically. Like we can look at the previous trend, and then we do some kind of forecast, and then the red line is the actual usage. So you can see that there's some small variation there, and the goal is to keep the deviation less than 5%. So that's the main goal of the capacity planning, which might not be that easy, but that's the goal we want to do. And I want to do a case study here. So even we plan very effectively, and then things still can go wrong in this case, right? This is a case study that we actually have a SEP1 instance. So one of our major service that is distributed across a multiple failure domain, we call availability zone, AZ. And then they are auto scale across a 3 AZ. But in this case, you can see the line there, that's each line responsible for 1 AZ, right? And then you can see that one line actually is far below. So that means actually this AZ run out of capacity. So that AZ the cloud provider is not able to scale up the machine for us. So that in the case that we cause the CPU bending and then actually overload one of our downstream service and cause the SR drop. So the solution for that definitely is to have a better planning so that we can have able to allocate enough capacity for all the AZ, right? So that's one case study that shows that capacity planning is very important. Okay, now that we have visibility, we have ownership, and then we have planning, the next step is to actually do something, right, with the action part. How do we proactively save money to achieve our efficiency and then the optimization goal? So I'm going to talk about 3 actions that we did to achieve the goal. So from the chargeback system that Micheal mentioned, that we have visibility of the different things, right, including the instance type. So instance type, we know that different instance type have a different cost. And then we did a project that migrate from C3 instance type to C5 instance type. We are on so that's the AWS instance type, right? But in this case, that the migration actually take a long time to complete because all the different service owner have to migrate it manually, and then they do it separately manually, right? And then it involve 30 plus team because at the beginning we all use C3 type, and then C5 type is much efficient and then larger and then cheaper, right? So that's the good thing about C5. And then that's why we might take a long time, a lot of resource, but we did achieve a very good efficiency gain. And in the future, that we are migrating the service into Kubernetes world. In Kubernetes world, we don't really need to worry about, from service owner point of view, we don't really need to worry about the instance type. So this will make the migration much easier to save. In the case that we need to move the other instance type to save money, then with Kubernetes, then the things will be much easier, right? So that's a good thing. Another thing is, another example is to look at the spot instance as well. So as we know that spot instance is much cheaper than on-demand instance. And then for us, we first step is identify the workload that is suitable to run on the spot instance. In that case, that we can migrate them and then reduce the cost of those services. So the second action we did is to maximize the auto scaling. So this is a graph that shows the number of parts of a service. So it auto scale according to the load. In this case, we specify by the CPU matrix. So we utilize the Kubernetes HPA, the horizontal part autoscaler. So we define the HPA policy that if the CPU is above 50%, then we scale up, and if it's below, then we scale down. So that's achieved this 5x part difference during the peak and then the downtime. And then another scalability is on the node level. So we use a cluster autoscaler. So it's also an open source CA. The CA actually the autoscale on the node. So whenever a pod is pending on the scheduling, and then there's no node available, then the auto scaler kick in, and we're going to we actually implement a buffer, right, so that it's not actually wait for not able to schedule, then we can scale up. We have a buffer so that we can scale up earlier than the actual need. So one thing we want to mention is auto scaling is a good way to achieve efficiency, right? But it also poses a challenge for planning, right? If you can see in the past slide let me see, you can look at the past slide. So in this slide, then, so that is the graph for the service, right? So you can see that we have a pattern that during the weekday, we have 5 days, you have a peak, and then during the weekend, so the utilization is much lower. So this pattern is pretty clear. But if you look at the node, so that's on the node side. So the node side, it does not actually clearly have these patterns. The reason for that is because we are using Kubernetes shared platform, a Kubernetes shared platform. We have a mixed workload on the same platform. So different services actually have a different scaling patterns, right? So when we do bin packing on the K8s, so the pattern is not clear. So this cause actually make the capacity planning much harder. So we don't really, it's not able to predict what kind of usage pattern that from different services, right? So there's something that we are going to look at our data and see what's the best model to do the prediction. Okay. Lastly, the third action that we do is to utilize the quota management. So as we know that K8s have the built-in quota management to make the quota management is by namespace, right? And then because we have a project mapping one-to-one to the identity map to a namespace, so we can easily to control that the quota for each project, right? So this is an example that you can do on the actual YAML file that you can specify on the Kubernetes platform. Then we can specify how many CPU we can allocate on this namespace. So for example, we have some development workload, right? We can put in a dev namespace so that this development workload run there, and then if there's run out of capacity, then it's not, the SLA for that service workload is not as important as the production workload, right? So that's something that the quota manager will help us a lot. Okay, so with that, I'll hand back to Micheal to have a conclusion to the talk. Thank you.
Thanks. So two things I want to call out is, I think they're working. Okay, perfect. So, can you still hear me? Okay, so two things I want to call out is, before I get into the takeaways, I think when we moved to Kubernetes, one of the first things we realized is everything is auto-scaling at this point. There was no way we could be like running multiple clusters and per use case, because operationally, that's just much harder for us. So we made a decision collectively to have a shared cluster. The intent with that was to make sure that as we are scheduling workloads on it, we have a more heterogeneous collection of workloads running on it, and we can focus more on packing them more effectively, at the same time leaving enough headroom for the Kubernetes cluster to grow or scale down. We've had a couple of incidents in the past where if they keep it too tightly, we've had run into risks where pods would want to be scheduled and the clusters just don't scale up more effectively. The reason we showed that step 0 is that no matter how much of our planning you do, there's no way you can always have infinite resources from your cloud provider. There's always some gap or the other, and that's something we should always plan for. So that was like one of the key learnings we had as part of that. So with that, like, I think the larger things for us was that it was very important. None of this would have been possible if we didn't have a good way of understanding how to tie ownership or identity to different aspects of our entire cloud footprint. it was very important to kind of group all of those things, regardless of EC2 instances or Kubernetes pods, get a clear view of how it's actually distributed across our cloud footprint. And part of that is only possible because we actually invested over 2+ years in getting that identity system integrated with multiple platforms within the company. Today, that has enabled us to like query and like group and do certain parts of planning simply because we have a canonical way of identifying anything and everything running on the cloud footprint. Literally, there cannot be any instance or pod running or even a bucket created without that particular unique identifier in place. So this is a must. I mean, this is like the biggest learning we could really recommend. And I know people have like used or tried to do this in different aspects by using tags and other features which the cloud providers provide. I'll be honest, like none of them actually work. We have tried that, and it's just over time, they get pretty stale, names change, and all of a sudden you have to write regexes to truly understand which clusters make up who. And that is something we just decided it's not worth it. So investing time into defining a spec, how can you like model your cloud in a way where you understand what region means or what a cell or a AZ means, and how do you want to like fan out from there from clusters to apps to pods was extremely beneficial for us. And we think that is something we can definitely contribute back to the community as a common spec to identify resources within the cloud. And the second thing is we realized that it was literally not a tools problem. It is literally a cultural problem. No matter how much ever tools we build, if those systems were not integrated and if the engineers themselves really did not adopt a lot of these best practices, there's no way we can get better visibility into who's running what in our infrastructure. Unfortunately, we have like so much of data, I cannot really show that much on the slide. But today, literally from our CFO to an engineering manager to anyone within the company can drill up and down into understanding our cloud footprint in all aspects of resources and everything. And this is only possible because it was important for us to educate what these things meant in a very friendly and in a very user-friendly manner. And this involved us, again, like multiple years of investment trying to like educate about the chargeback system or about what identity actually means within the company, and then subsequently generating reports, notifying people saying that you've used XYZ resources, and investing into a single pane of glass UI as well, where if you're starting a new project at Pinterest today, you'll actually go through that UI first, which will ask you a bunch of questions before your entire project is actually set up. And as part of that, all the identifiers are set up and they are like distributed across our entire platform. So clearly, that was a huge change for people in the past who would just use the CLI and spin up thousands of instances. And yes, I'm sure it must have happened for multiple people here. And yes, we have spent $100,000 or more just by losing or getting into that run. So this is a big thing, and these things do take time. But when you build the right tools and systems and you have the right guardrails in place, I think we can really make a difference in terms of moving into the space. I think with that, finally, I would just like to say thank you. Thank you for spending the time with us today. And yes, if you do have any questions, we're happy to answer offline and even show some other information we have. But yeah, thanks a lot.